Welcome back to linear algebra. Let's jump into Anki. All right, here we go. What can you say about the number of solutions of a linear system ax equals b for which the coefficient matrix is invertible? What can you say about the number of solutions of a linear system for which the coefficient matrix is invertible? Has exactly one solution. How many different inverses can an invertible matrix have? One. Is it possible to multiply two invertible matrices of the same size and obtain a matrix that is non-invertible? No. What must be true about the matrix A for the products A times the transpose of A and the transpose of A times A to be invertible? What must be true about the matrix A? I don't know. It's either the products are invertible or the matrix A is invertible. Isn't the transpose of an invertible matrix invertible? I'm not exactly sure. I would say what must be true about the matrix A for the products A. Oh, A must be invertible? Products must be invertible. That doesn't make any sense. What must be true about the matrix A for the products? That doesn't make any sense. I must have typed it in wrong. So A must be invertible. Only if you want both A, yeah. Okay, so it's not products, it's A must be invertible. Okay. Suppose that A is an invertible n by n matrix and B1, B2, Bn are n by 1 column vectors. What information does the reduced row echelon form of the partition matrix A, B1, B2, Bn provide? What information does the reduced row? It provides the solution to AX equals B1, AX equals B2, AX equals or AX dot equals Bn. You haven't recorded your voice yet? There's some kind of voice recording on this. The last n column vectors in succession are the solutions of the system. AX equals B1, AX equals B2, AX equals Bn. State 5 results that are equivalent to the statement that an n by n matrix A is invertible. Okay. 5 results. A can be represented as a let's say AX equals 0 only as the trivial solution. Then we can say what? A can be denoted as or represented as a product of elementary matrices. The reduced row echelon form of A is the identity matrix. It's going to be any and every solution. Something along AX equals B. There's a solution AX equals B for every column vector B. There's a solution for every column vector B. That's the correct size. Or any. How does this work? Every and any. AX equals B. So there's like for every B, there's a solution. And for for any B, there is a solution, and for every solution B, there is exactly one solution. Is that it? AX equals B is consistent for every n by 1 matrix. AX equals B has exactly one solution for every n by 1 matrix B. That's right? I would say basically it's right. What is an invertible matrix and what is another name for such a matrix? It is a square matrix in which another square matrix exists that it commutes with, and their product is I. And another such name for such a matrix is non-singular matrix. Square matrix in which another matrix of the same size commutes and their product is I. Another name for such a matrix is non-singular. Okay. All right. I'm going to jump back in. Actually, I'm going to grade what I did yesterday. And then we'll go from there. So I'll be back in a second. Okay, so I actually graded yesterday's problem. 21 was good. I was going to look up how to do 23 because I couldn't figure it out yesterday. But then I was like, let's just see if overnight I figured it out. And I did. I figured it out. So I just showed, we were showing that it wasn't a matrix transformation via the theorem, basically saying that a matrix transformation is a transformation is a matrix transformation if and only if it has the additivity and homogeneity properties. And so I was like, okay, well, if I'm just showing that it for all u, v, k, that additivity and homogeneity properties don't hold, I just have to find one counterexample. And so I just put some random numbers in and was able to show that they weren't equal, and the additivity property does not hold, therefore it is not a matrix transformation. So solid there. I'm going to continue working now and be back to recall what I did in a little bit. All right, I worked on a problem from 1.5 today. I need to write that on there. 1.5. It's writing an elementary writing a matrix, which was originally this, as a product of elementary matrices, as well as writing its inverse as a product of elementary matrices. And so that's what I've been working on here. First, finding the inverse, and then I believe I take the matrices in backwards order. I think. Oh, no. I take basically an elementary matrix, so in backwards order, I believe. So this would be for multiplying -1 through row 2 up to row, and adding it to row 1, we'd say the first matrix, I believe, is 1 0 0 no 1 -1 0 0 1 0 0 0 0 or 0 0 1, I should say. That is an elementary matrix. I think it's going to do it backwards order. Tomorrow I'll actually try it, and then I'll multiply it through to make sure it's the original matrix. And then for getting the inverse as a product, I'll have to figure out what that, maybe they'll be going this way. I'll have to figure it out. I'll be able to figure it out though, I'm pretty sure. So that's it for today. Talk to you tomorrow. See you.